In the third part of today's lecture, we will learn compound interest. That is a very, very important topic, not only of this chapter, but also of this course. So please pay special attention to this part of video. First, the definition. So let X be the amount of dollars invested in an account that pays compound interest at a rate of I per year. Then the accumulated value of this investment account after T years is given as X times bracket 1 plus I to the power of T. So this tells us how account value will accumulate over time, right? Remember, for simple interest rate, let me write down here, for simple interest, the corresponding accumulated value grows as X times 1 plus Ti. So different forms of interest lead to different formulas of AV value, okay? So here it is in power function form, or you can, right? Of course, you can also convert to exponential if you want. Remark, please make sure, okay? So here, the interest rate and your time span have the same unit. In most of the time, we will have time unit as 1 year, or time unit of year for the interest rate, but sometimes T is not in the unit of year, so we will have to convert it into the unit of year, which we already did in the simple interest section. Say here we have a short example, say the current monthly interest. So here the monthly interest rate is 1%, and we're going to apply compound interest. What is the AV of $100 in 5 months? So here, because our interest rate is quoted in the monthly basis, and here the time span, or T, is 5 months. They actually have the same time unit. That's why here is 5. You do not need to convert this into years. However, if I tell you the interest rate is 5% per annual, still the same question, but now we need to convert 5 months into years, and there are 12 months in a year, so T is given this form. Then your AV at T will be 100 times 1 plus 5% to the power of T, which is 5 over 12. So just remember the interest rate and time T should be quoted in the same unit. If not, you need to do the conversion, okay? By the way, this is not common in this course, right? It's rare I will give you a monthly interest rate. That's why. So here it's only for illustration purpose. 2 important observations. First, according to this formula, the formula here, okay? Apply this formula to AV T plus 1 to AVT, okay? You can think T as number of years. So from T to T plus 1, you move forward by 1 year, okay? You get this to be 1 plus 5. And it is independent of T. This is true for all T, which means if you apply compound interest rate, the final interest you will be getting is this, okay? So not 1 plus I. This is here's a typo, because if you do this, it will be 1 plus I minus 1, so it's I. So this formula is important because it says that if you apply compound interest rate, okay, or compound interest, the corresponding interest rate over any year is the same. So if you apply compound interest rate to any time for 1 year, you will get the same interest rate, I, and it is independent of t. It is independent of t because the result is simply I, is the same, right? So it's independent of t, okay? Here is a typo. Let's cross this out. That is a very good result, because from there we can claim that compound interest rate is simply the effective interest rate, because it's the same. It doesn't matter where you start, as long as it's for 1 year, the rate is the same. It's a very nice property, right? The second one, in the case of compound interest, earned interest accumulates further interest. That is very, very different from the case of simple interest. Remember, in simple interest, only the principal part will earn interest. But in the case of compound interest, interest itself will earn future interest. So the ball is rolling at much faster rate, because interest rate is rolled in, but in the simple interest rate, interest is out. Okay, you do get the interest rate, but the interest rate does not make your principal bigger. But in the case of compound interest rate, in each period, the earned interest is rolled into the principal. You can think it that way, because the effective principal becomes larger, but that is not the case in the simple interest rate. That is why here it is very, very important to notify that. Okay. Remember let me add a page. Okay, I will give you some mathematical results. So now let's separate. On the left-hand side, we have simple interest. On the right-hand side, we have compound interest. Okay? So by definition, this is x times 1 plus I. So basically, I'm doing a side-by-side summary of the two interest rate forms we have studied so far. So let's calculate this. Okay, by very, very simple calculation, we get this. Okay, so this is fixed, right? Which is a fixed number. So in the case of simple interest, the amount of interest over 1 year is the same. Okay, it doesn't matter when you start. Here the starting point is t, and the amount is x times I, which is fixed. So it doesn't matter when you start, when you end, as long as the time span is 1 year, we know the amount of interest must be the principal times the interest rate. So that is fixed, okay? However, the rate of interest is not. Over 1 year is not the same, because it depends on the starting value, right? So if you want to calculate the interest rate, it is the difference divided by AVT. So if we write it down, it will be x times 1 plus ti. So let's cancel x. Right? So what we can say, so as t moves forward, or as t grows, the rate actually decreases, right? That is because the amount is fixed. If your denominator is growing, it's becoming bigger and bigger, the ratio will become smaller and smaller, right? So that is why here I mentioned that only principal here's a, I didn't write it correct. So let me erase this. Only principal will lead to interest. Okay, so that's why here the amount is fixed. Okay, but now we already did. If we do a side-by-side comparison, we know this amount. So let me emphasize. Is not the same over all t. However, the rate is the same. Okay, the reason why the rate is the same, we already proved in this very easy formula. So the rate is the same I, right? So rate is the same I, but amount is not the same, right? So the reason, again, it's simple, because if you do the calculation, you will immediately see the result, right? So it will be x1 plus I t plus 1 minus x times 1 plus I to the power of t. Of course, we can factor out AVT, right? This is exactly the result. So obviously, this amount depends on t, right? However, the rate is independent of t. The rate is I, because we need to divide by this guy, right? Then it cancels. It only leaves I, which is a constant independent of t. Okay. The reason behind that is, in this case, both principal and the previous interest, both will earn future interest. So that is why the amount is not the same, because your base here is becoming bigger and bigger for a larger amount of time, right? So that is, I would say, this comparison table is very important for you to understand the difference between simple interest and compound interest. Okay, we have this calculation example. I ask you to calculate when x is 100, interest rate is 5%. Of course, it is, well, assume it's per annual. Okay, by applying the formula here and here, you should be able to get the result relatively easily in this. I only did 4 calculations. You should definitely do more. If we compare side by side, this is greater, right? This is equal, and then left-hand side is less than right-hand side, left-hand side is left-hand side, and the difference actually becomes bigger and bigger. So what do we claim? So here we have 3 scenarios, right? At this, simple interest rate is equal to compound interest rate. When time is between 0 and 1, simple interest rate, I mean the accumulated value at simple interest rate is actually bigger than compound interest rate. For more than 1 year, simple interest rate is less than compound interest rate. So now, for us to better understand this result, let me draw a graph. Okay. So let's say here's, well, let's just do 1. Okay. So to make things slightly easy, let's say the principal is 1. Y-axis is AV value. X-axis is time. This we already know, right? This is simple interest rate. Now let's draw the graph for compound interest rate. So assume here's 1, okay? Then we know this is 1 plus 9. Okay, let's try another color. Use brown. So this is, of course, my drawings is really bad, but it somehow represents the compound interest rate, right? Because under the compound interest rate, the cumulative value is a power function. So it somehow grows like this, right? So from this, we immediately see everything we summarized from here, right? We have 2 points at which both lines cross, right? So they intersect at time 0 and time 1. So there are 2 points. The AVs are the same for simple interest rate and compound interest rate. Between 0 and 1, the pink line of the simple interest rate is higher than the brown curve of compound interest rate, right? Beyond 1, compound line is much higher, and if you look at the difference, the gap actually becomes bigger and bigger, right? So we already know the result for both of them. It's x. So those are in relatively simple functional form, right? So if you want, you can actually prove this mathematically. So give it a try if you want to test your math skill. Okay. There are several examples from the textbook. There are 3 examples, 1.5 to 1.7. Let me take a look. So example 1.5 is basically to demonstrate that under the compound interest rate, okay, there is no point of taking the money out and withdraw again, because interest rate itself will give future interest rate. But if you want, you can do a quick calculation, right? So the first guy is Wendy. Wendy deposits $100 at the interest rate of 6% for 2 years, right? Which is $112.36. Okay. There's another guy, Leonard. Leonard does deposit for 1 year. You get the value, which is obviously 106, and he makes another deposit for 1 year, right? You get the same result, obviously, right? So in the case of compound interest rate, there's no point of making a lot of visits to the bank, trying to take the advantage, because there's no advantage. It's the same, okay? Example 1.6. Carmen borrows $1,000 for 90 days. At an annual effective interest rate of 8.25%, what will the total payment be in 90 days? So we are going to convert 90 days into the number of years. Usually, if you don't see any specific rule, assume that there are 30 days in a month. So immediately we know this is 3 months, right? And obviously there are 12 months in a year, so it's a quarter. And AVT is easy to calculate, right? 1 plus I. Okay, we raise the power to 0.25. Okay, so you can easily get the result. 1.7. Okay, 1.7 is slightly different. Okay, this deserves more attention. Sam borrows $2,000. So Sam borrows, not $2,000, $20,000. He repays the loan in 4 years. So we know he's 4. By the way, I highly recommend you to follow my steps. You see, in each and every example, whenever I read a piece of information, I'm going to convert that information into mathematical notation, using the standard ones. For example, the first sentence says, Sam borrows $20,000. That means the principal is $20,000. He repays the loan in 4 years. So I know the time span is 4 years. With the repayment, so I know by the end, the the value of this loan is $26,000, $709.38. What I want to calculate is what is the interest rate per annum, right? This is basically the reverse engineering, because usually we know the interest rate, we know time t, we want to know the future value. Now we know the future value, we want to go backwards. So we establish the same kind of equation. 1 plus I, I'm missing a 0. So now the reason why I ask for a little bit more attention is some of you may have issue solving this equation, because this is an algebraic equation. In order to solve this, first of all, we divide by 20,000. So we divide by 20,000. By the way, you can get a value, which is 1.335,469. By the way, please do not write this down. I'm writing this down to basically show you how it is done. If you have a scientific calculator, it can record the value. Okay, keep it. So now I have so I'm trying to solve for I, right? Here it has a power term. So in order to get rid of the power, we should take logarithm on both sides. So let me use introduce a constant c. Okay, so I don't want to write this long decimal. So let's take logarithm, right? So this is a power, and power in log function will come out, right? So this is one of the rules of log function. So now I should divide by 4. I get log 1 plus I. Again, I'm aiming at I, but I is inside the log. How can we get rid of log? By taking exponential. Okay, finally, I know my I is e to the power of log c divided by 4 minus 1. Okay, and you should get the final result in one step. You don't need to record all the numbers, right? Because you can type in this number and then divide by 20,000. You will get this constant c, which is 1 point something. There's no need to record. You can directly hit the log function on your calculator, right? Then you will get log c, and then you can further divide by 4, get another number. Again, no need to write it down. There is an exponential function in your calculator. If you are using Texas Instruments BA2, you need to hit the second button, right? Because exponential is on top of log, right? And then you hit exponential. It's actually ln, because on top is exponential, right? So we get the exponential is this term. Again, no need to write it down. We can simply subtract 1 from it to get the final result, okay? And if you want, you can times by 100 to get into the percentage. So it's 7.5%. So we still have 2 slides to go, and it's likely that I will slightly go over 75 minutes. Of course, I will keep an eye in the future in tracking of time. So next, I want to talk about the frequency of compounding. In all the previous slides, we assume we compound once a year, okay? What if we compound more often? Let's say we compound every 6 months, or we compound every month. So what would that make a difference? A short answer is yes. Remember, in the first part of this video, I asked you to check on the simple interest rate, right? So now there's something slightly, they share something similar, but they're also different, okay? Here, what we do is, so how about we take a look at this definition? Let IM be the annual nominal interest rate. Okay, we will get to this later. Compound m times a year. The accumulated value of x from time 0 to time t is given by this formula. So this is the formula of AV when we have a compound interest rate I, but it is for m times. Okay, of course, when m is 1, it goes back to what we used to know. How about let's try m is 2. M is 2, which means we compound every 6 months. So in 1 year, what do we get? So we divide it by 2, raise the power to here is 2, and since we just want 1 year, so it's so let's break this. So this squared, right? So this is different from what we used to have for 1 year, right? Because if we, in the past, what do we have? We have this for 1 year, right? Because this one. Now we have an additional term, and obviously this term is positive, right? So using this example, we easily see that by compounding twice a year, you will be receiving more. And of course, if you compound even more often, let's say 4 times a year, every quarter, you will receive furthermore, because every time when you expand a polynomial or the perfect, let's say to the fourth, you will get more terms, right? More terms, they are positive. All of them are positive because I is usually positive, right? The additional positive terms means the accumulated value is bigger, right? So a quick intuition is that by compounding more, one will receive more over the same amount of time. To make this more precise, we actually have this table, okay? So we assume I is 1, nominal interest rate is 5%. If you compound, we get this, right? So here, let's talk about what is the difference between nominal and effective. So remember, in here, we call this a nominal interest rate. And what is the difference? So what is the effective interest rate using this simple example? If I want to know the effective interest rate, that is, in this case, let's move here. So I use this minus AV0 divided by AV0, right? This is how we calculate effective interest rate, right? So a simple calculation shows that right? So it is actually bigger than this. So the effective interest rate is actually higher, which is not surprising if you look at those numbers, right? So 5% is the nominal interest rate. Okay, if the effective interest rate is also 5%, you will be getting exactly 1.05. That's in this case, right? As in this case. But as we can see, as n gets bigger and bigger, you will earn more, right? You get higher number. What would be the limit, right? When n goes to infinity, what would be the amount you will be getting, right? So a short answer is you will get exponential rate. So here is just a 1. So you can check what is this number. Okay, this is eventually the limit you will be getting. Okay, so I think I will stop here, and in the next week's video, we will continue in this chapter. Okay.